Continue.
Thank you. So yeah, this is the second lecture in trying to understand how to get classical physics out of quantum scattering amplitudes. I've already discussed the motivation last time. I should mention it was put up in the Slack channel, but a lot of the material here you can find in my paper with Donald O'Connell and Ben Mabey. Ben actually may be in the audience. So, that's on the archive. So the key points from the previous lectures, first of all, that we should be looking at observables and looking at observables in the quantum theory that are meaningful in the classical limit as well. And the one that we picked as an example, and probably the only example we'll look at in these lectures, is the change in the momentum of one of the particles, which is known by the impressive name of the impulse, the classical impulse. We had to reintroduce h bar, of course, in order to be able to take the h bar goes to zero limit. And the first thing that we had to do there is to put it into the coupling, make it manifest in the coupling. And we also wanted to distinguish wave numbers from momenta, and it will be helpful to introduce the barred notation for that. We defined our incoming state for the scattering. Again, we're looking at the scattering of two particles and then the 2 point particles, massive point particles. And we're writing their state in terms of a phase space, an on-shell phase space integral over the two incoming momenta. There are wave functions, which are essentially allowing us to express these localized particles in terms of plane wave states, the plane wave states P1, P2. And then there's a phase factor, which takes into account the fact that we're not shooting these particles directly at each other, but there's an impact parameter. And we derived a general all orders formula for that observable in the quantum theory. So this is a quantum observable. You could calculate it there as well if you were scattering not just in the classical limit. There were two terms, and we saw in the last lecture how to give a diagrammatic interpretation and the connection of the first term to the amplitudes. Why my pen is slippery this morning. So this was the I1 and I2 terms. And I'm in parallel with the school attending a conference, and I'm starting to notice that this jargon is becoming a shorthand, the I1 and the I2 terms. So you may encounter it in the future as well if you continue to work on this subject. The I1 term was linear in the scattering amplitude, and the I2 term was quadratic. We wrote down an expression for each of those two terms, but we didn't, I left it as a homework exercise to write down a diagrammatic interpretation of the second term. And we will see in a couple of minutes what that is. So the form we'll actually be working with for the first integral, again, of course, it has that oops, that's not actually needed. The space measure is universal. Yep. And there is this momentum mismatch, which from the amplitude point of view looks like a momentum transfer, but is really a mismatch between two different copies of the initial state. And again, the hat notation kind of cleans up some of the pi's that are floating around. Data functions, which don't really play much of a role in classical limit, but I will write them for completeness. And of course, the thing that we're actually measuring is the momentum here implemented by the momentum mismatch. And then we have an amplitude. And that amplitude, of course, instead of just having trivial external wave function factors, has these wave functions that build up the initial state. There are two copies of them slightly shifted. And that slight shift is what is going to control the classical limit. So the formula we had written down for the second term involves a sum over additional particles, which that sum could, of course, be the sum over nothing. So that would be the lowest order contribution in the second term would have an x that we now have the integration over the genuine final state momenta, which here are called R sub I. And again, we have the same kind of momentum transfer factors and delta functions and theta functions, which I won't write out explicitly. They're written out a few lines above. The formula that we had, again, had the wave function factors, and which I'm sure by now you have memorized, and I could abbreviate. We have the same style of phase factor, and this time we have what really looks like a final minus initial state momentum. That's the observable we're actually measuring. There's an overall energy momentum conserving delta function, and it has exactly the form that you might expect. So again, Rx here stands for the momenta of all the additional particles that might be present in the initial state. Of course, there's both a T dagger and a T, so we've put in that intermediate state, and we now have a product of two amplitudes. And again, these amplitudes are starting from the different copies of the initial state, but they're ending up in the same final state. So here we have P1 plus Q, P2 minus Q, but going into the same genuine final state. So that's where we left off. And it's now convenient to introduce what are genuinely momentum transfers. We'll call them WI. At this stage, we're still working with momenta, not with wave vectors. So these are the genuine momenta that are transferred. There's actually going to be two of them because in general, since they're because of the additional radiation that can come out. So we can write out the modified form that one gets after changing variables to the WI. And again, I'm going to skip over the parts that you already know. So we have the kind of measure factors for the initial state, and now the final state we've traded for the these momentum transfer variables, and of course we have the D4Q. Those delta functions that are associated with the D4Q, I won't write out explicitly. We have a set of on-shell delta functions from the final state momenta, from the RI variables, and those leave behind these sorts of delta functions. And again, there's also a theta function because those are really delta pluses. So we have the deltas that are associated with Q and the thetas that are associated with Q, and those you've already seen on previous lines. And we have the usual wave function factors that we've seen above. Don't need to write those out explicitly. And I think I may have dropped some signs in various places, so apologies for that. And it's now exactly the momentum transfer, in a sense, that is the variable that we're measuring. And the delta function, once we've changed variables, takes this very simple form. And you can see right away that in the simplest case, where Rx is simply absent, so it's 0, then it's going to allow us again to integrate out, let's say, W2 in favor of W1. And of course, we have the amplitudes, again, the two different copies of the initial state. And going into the same final state. So we can give a diagrammatic expression of that. And let me just write out all the upper part here, of course, is going to be the same. So I'm not going to write that out again. Let me just write out the diagrammatic representation of the last line. Well, actually, I guess I'm going to include the wave function factors in this diagrammatic representation. So we have two amplitudes, an optional additional momentum Rx. So here we have the wave function factors for the two incoming particles. And of course, we have the conjugate process on the other side. So we have P2 plus W2, and it's exactly the same momentum that then flows into the conjugate. And then we get the wave function from the second copy. And let's see if I can actually manage to. So these things are, again, they're all ordered formulas. So you should imagine that these include both loop And of course, they also include real emission corrections, because although I've drawn a single additional messenger, that really stands for an arbitrary number of those. So I hope this matches the formulae or the pictures that you draw as you drew as part of your exercise. So the next task, I mean, if we were trying to do the computation in the full quantum field theory, we would just go ahead and compute this thing, and we would end up with some result. It's a perturbative expansion in G, so in E for electromagnetism, or in kappa for gravity. But we now want to, and then one can imagine doing that and then taking h bar to 0 at the end. But that, of course, would involve computing a lot of stuff that is ultimately getting thrown away. So the next task we need to look at is how to get the classical limit of these expressions. And of course, so far I've treated this wave function phi, little phi, as a black box. And so now we need to start thinking about specific forms for little phi. And one can actually do this argument without having to choose a specific form, just choosing kind of a class of forms. But it's actually helpful, I think, to look at a specific form and understand a little bit more in detail how it works. But before we do that, we should think about the scales in our problem. So what scales do we have? We have three scales, really. And the first scale is the Compton wavelength of our particles. And we can imagine, for the sake of the argument, that there's no big difference between the masses. I mean, there would be, in general, so that the Compton wavelengths are comparable. Of course, in general, one would have two of them, and the arguments that I'm going to give would then have to apply to each of them independently. So that's h bar over mi. And of course, to take the classical limit, we're going to try and take these Compton wavelengths to 0. There's the wave packet size. So we want something that's of course localized, so it's going to be characterized by some length, and that I'm going to call L sub w, the wave packet size. And finally, there's the actual impact parameter. And you can think of that as kind of a scattering length. It's something that it's a characteristic scale of the scattering. And so this thing is B, or sometimes I will refer to it as L sub s. So this is actually going to be a 4-vector in its origin, being u. We've already seen it appearing in the formulas. And it's something that's necessarily space-like. So you should think of it as just being, at least in the appropriate frame, it's going to have a 0 time component, and then it points in some direction. If you want to have the two particles moving along the x-axis, you could choose it, for example, to be in the z direction. So, of course, we want to do this in a relativistic setting, but it is, as I alluded to in a response to a question in the first lecture, it is convenient to start thinking about a non-relativistic wave function. And so if we want a minimum uncertainty wave function, then we would write down some kind of Gaussian. So we might write down something like the exponential of minus p vector squared. So this is again a 3 vector now. And maybe something like this. And we would have some parameter that is a ratio of these two length scales. So you're probably more used to seeing these in position space because that's usually how quantum mechanics is done in introductory lectures. And that would correspond to a Gaussian wave function, which has the form something like this. I don't promise that all the factors of 2 are exactly right. And so that it has something which has a characteristic, it's a lump, which has a characteristic size of LW. It tells us how well we really know the particle's position. Now, in a relativistic quantum theory, the notions of a particle's position is not really well defined, but we can still use something like LW, or in fact, the variable LW itself as a measure of how well localized the particle is. So we want to be taking the h bar goes to 0 limit, and in our present context, that's the same as taking the quantum wavelength to 0. On the other hand, we want to make sure that the particles are localized. And so that says that we're also going to take this wave packet size to 0. At the same time, we want the quantum effects to be less and less significant. So this is also a ratio that we want to take to 0. And as you might have thought from the previous transparency, it'll be convenient to define a parameter, which I'll call C, dimensionless parameter, which is kind of controlling this limit. And we can take it to be LC squared over LW squared. So C is actually of order h bar squared. And so if you see square roots of C, those are still natural expressions to appear. If you see the 17th root of C, you might wonder what is happening here. So square roots are good, other roots are not so good. Now we have our two wave functions, which are going to be very well localized, so they have to be well peaked, not necessarily quite as sharply peaked as that drawing would indicate. And their separation should be also much larger than anything to do with their internal structure, anything to do with the size of the lump. And so that says that we're also going to want to take the ratio of the wave packet size to the impact parameter, to the scattering length, to 0. And so qualitatively, what we're expecting is that we need to impose the conditions that the Compton wavelength is much smaller than the wave packet size, and in turn is much smaller than, whoops. Okay, let's see if I can, let's just ignore that. Hold on a second here. Is much less, so the Compton wavelength is much smaller than the wave packet size, and in turn is much smaller than the impact parameter, which is kind of what you would think of as a scattering length. And this is what we called in the paper the Goldilocks conditions. So one, as I mentioned, one could analyze this in a general class of wave functions, but it's more helpful to see how it works in a concrete example. And as I'm showing this concrete example, of course, you can keep in mind that I could well have chosen this specific wave function and done the calculation with it. So we want to exponentiate probably, or we want to have some function that is Lorentz invariant. So we need a Lorentz invariant quantity. And the only 4-vector we're starting with is p for a single particle. And we can't build a wave function out of that because the only Lorentz invariant we have is p squared, and that's a constant. So that's not a good thing to integrate over any sort of phase space. We need to introduce another 4-vector, which I will call u. And at the end of the day, u will turn out to have the interpretation of the classical 4 velocity. And so it's convenient, in fact, to choose its normalization to be 1. So in a center of mass frame, it would just have the form 1 with a 0 vector. So that gives us one non-constant invariant to play with. And of course, we want to make it dimensionless so that we can build interesting functions out of it. And we also need some way of controlling the limit. And as we saw in the non-relativistic example, we're going to have something where that limit, the C parameter is going to 0, and that's going to maybe make the argument of the exponential diverge, and that's going to cause the exponential to localize. So that suggests that the quantity, we should try and build something, some function out of this ratio, p dot u over mc. It's dimensionless, and it has a appropriate limit as c goes to 0. So the simplest function that one can build, in fact, turns out to be a very suitable function. There's some normalization, and I'll make this normalization factor dimensionless by removing a factor of the mass. And it's just an exponential of minus this basic quantity, this basic rescaled invariant. Now, your non-relativistic intuition tells you that this is nonsense, because if you have a single exponential, surely, yes, it will have nice tails somewhere, but it will also blow up in other directions. And in fact, relativity here saves you, because if we, for example, boost to the rest frame of this 4-vector u, then the argument of the exponential is becomes minus m squared plus p vector squared, the square root of that, divided by mc. And that thing is, in fact, strictly negative. So in all directions, it will be fading away in all directions in the p vector space. And that's essentially what we're integrating over because of the on-shell condition in the measure. And in fact, if you expand this in the non-relativistic limit, you see that we get a Gaussian. So in fact, the natural generalization, natural relativistic generalization of a Gaussian is just a simple exponential.
Sorry, can I ask a question? So,
yes.
So what vector was u again?
So u, at the moment, it's just an arbitrary 4-vector that I've chosen with a normalization u squared equals 1. And in order to give you a little bit of intuition, I'm telling you that at the end of the day, it will turn out to have the interpretation of the classical 4 velocity of the particle.
I see.
You can sort of see that here already just from this discussion, because what's going to happen is that we're going to peak the we're going to peak the 4-vector p more and more closely around something, and that something is going to, in this frame, is going to make the p vector, the 3-vector, vanish, and so p is going to be essentially proportional to you. So of course, as you're peaking the momentum more and more closely in the classical limit, you're ultimately getting the classical momentum of the particle, and you divide by m, then you're going to get the Four velocity.
Okay, I see, thanks. And another question maybe, that we had this LC, and this is the Compton wavelength of the particles we are scattering.
That's right. That's right. I mean, as I've said, I said initially, and I did in fact put indices, there's really two different Compton wavelengths because there's two different particles, they have different masses. But for the purposes of this exercise, let's take those masses to be comparable. So the Compton wavelength, there's no big hierarchy between the two Compton wavelengths. Of course, that Compton wavelength is independent of any knowledge of the wave function. If you could have some very fluffy particle and it would have the same Compton wavelength.
Mm-hmm. Okay,
so we can now ask, we want to have some measure of what happens to this wave function in the limit that c goes to 0. And one way of understanding that is, of course, the momentum squared is a constant, but it's a useful normalizing factor. So we can measure the spread of the momentum of the particle and just normalize it by the momentum squared or the mass. And this is a straightforward calculation to do. I encourage you to go off and do it. And you find that there's the following expression. You have to dust off, at least for a particle physicist, you have to dust off some mathematical physics books, not so much to do the integrals as to remember what the functions that emerge are called. And the k's are what are called modified Bessel functions of the second kind. And I'm sure since most of you are much closer in time to your mathematical physics courses than I am, you may have known this right off the bat. You might even know why they're called the second or first kind. Anyway, a little bit of the 19th century history that is tagging along. And if we now expand this in the limit that c goes to 0, we find that this goes to -3/2 c plus something that's of order c squared. So we see indeed that the spread of this wave function in momentum space is narrowing as we go to the limit. So in fact, this is a suggested exercise. Obviously, there'll be no corrections. So do this calculation explicitly. Okay, so now the question is, all right, we have a candidate wave function, and one could imagine plugging it in and doing the calculations explicitly. But of course, since we're doing a scaling limit here, we want to understand qualitatively what's happening so that we can simplify the calculation. And of course, the ultimate goal is to have these wave functions recede into the background and not really play an explicit role in any calculation, in any practical calculation. That's what you'd expect. I mean, we're not concerned about the quantum mechanical structure of the classical particle. So let's first look at a toy integral as a warm-up exercise, and call it T1 for toy. and it's just a single momentum integral. So but we're going to look at an overlap of two wave functions with this additional delta function. So we're going to plug in our exponential. We have an explicit form for phi of p. And I'm also going to kind of jump the gun a little bit and change variables to our wave number variable. And we'll see a posteriori why it makes sense. Of course, it's just, I guess I should put in a d hat for q here. It's, of course, one is free to change variables as one wishes, but this turns out to be a convenient thing to do. So now we have a 1 over h bar m. There's an eta of q bar p, which I'll tell you in a minute what that function is. We have actually let's leave this aside for the moment. So let's get rid of that. And let's just focus on the p integral. And so now we have 2p dot q bar over m. And the factors in front come just from rescaling the delta function, and h bar q squared over m. And because it's an exponential, then I get to have the nice feature that I can remove a factor. The exponent is linear, so the p plus q actually factorizes, and the term that's left over is exactly phi star of p. I mean, of course, that would not be true for a different choice of wave function, and then you'd have to do a much more detailed analysis. And now we can actually evaluate the remaining integrals in P. And what one finds is that, let me write out the formula first, and then we'll look at it a little bit. So we have some numerical factors, the factor of h bar m. We obtain q bar dot u squared minus q bar squared. It's actually the square root of that quantity. There is a Bessel function, which is coming from the normalization of the wave function. And this eta, again, is of course, just an exponential from that because it's the exponent is linear. And now we have a more complicated exponential that involves the same square root. So q bar dot u squared q bar squared. The pen is misbehaving this morning. I don't know why. And that's, of course, dimensionful, so it has to be normalized by something. And that normalization factor is just the square root of q bar squared. And then there is there's still a surviving second term, which I've retained for the moment. wondering if this is an overheating issue, but anyway, we'll take a short break. While this is also square root. This is all sitting, come on. Okay. It's all sitting inside the exponential. And of course, we should note that q bar squared, again, is going to be a space-like object. So minus q bar squared is perfectly positive. There's no hidden imaginary factors in here. So that brings us to the next exercise, which is to show this explicitly. So do those integrals. Now, as we take c going to 0, we expect that this thing will be concentrated. That's going to be happening because of the 1 over c inside the exponential. And we can see that a little bit more explicitly by kind of simplifying some of the structures inside. And the first thing to do is to simplify the Bessel function a little bit. We can, in this limit, we can write the Bessel function in front as being something like having a square root of c, and then there's an exponential of 2 over c. So what's going to happen is that that's going to combine with the other exponential, and it's going to force it's going to localize the numerator. Now, there's an h bar in front, and of course, remember that c itself is of order h bar squared, so so that h bar times root c is actually of order c. So that's of order h bar squared again. So the integral that we have has the structure of 1 over c times the exponential of some function of q bar divided by c. And this thing has exactly the right structure to become a delta function of essentially a delta function of something like f of q as c goes to 0. So again, it's going to localize, and then in turn we will then have that delta function to play with when we're doing the q integral. So one can work in the rest frame, again in the rest frame of u. So work in the rest frame of u, and we can then parameterize q bar as follows. There's some overall scale, and then there's the time component, which you can write in terms of sinh zeta, and then there's some directional component, which we can write in terms of cosh theta. And the exponential will then take the form something like minus 2 over c times cosh, and there we have to keep track of the term coming from the normalization. So there's a cosh of zeta, and we have our 1 plus h bar squared, q bar squared over 4 m squared, square root of that thing, minus 1. And if we set aside this h bar squared term for a minute, then what that's going to do is essentially localize q dot u. So we're going to get something like a delta function of q bar Now, there's a plus order h bar squared, which you might think one can just toss away very casually. That's not quite true. So I'm going to oscillate between ignoring it and reminding you that you do need to keep track of it. And I'll mention why a little bit later. So this peaking is going to force the, it's essentially going to force h bar over m times q dot u. I'm just writing out the thing that we have. So the argument of the delta function is being forced to be much smaller than the parameter c, and that corresponds to q dot u times LW being much less than the square root of c. So let's keep track of that equation. I'll call it constraint number 1. And so, of course, we're considering a much more general situation here. We have a function of 2 momenta, and there's a complicated amplitude that enters in, but that amplitude is going to be slowly varying on the scale of these wave functions. So the result of these integrations is going to single out some that will give us this constraint, and will also give us some other dimensionless ratios, and these are going to be things like the Compton wavelength times minus the square root of minus q bar squared, and something that you already saw explicitly in the integration. There's now 2 4 velocities. You saw it in the integration of 1. And so this is what we're going to find. If we call this thing the scattering length, then we'll see later that it is roughly going to turn out to be of order b. It's essentially couldn't be anything very different since there's no other dimensional scales. So we have additional these dimensionless ratios that we're keeping track of that are coming out of the integration that are essentially this Compton wavelength divided by this scattering length, and also these the dot product with the momenta again times the scattering length. So the function that we're computing is essentially going to be polynomial in these ratios. There's going to be some angular averaging that is happening inside both the momentum and the q integrations. And so what's going to happen is that, again, the q integration is going to localize these ratios, and they're going to end up being less than some power of c. And it turns out that the loosest constraint that we would get is if we assume the lowest reasonable power, namely the square root of c. If we get them to be localized by the integrations to a higher power of c, that's a stronger constraint. So this is the weakest possible assumption. So these are going to be constrained to be of this order, and we can call this the second set of constraint equations. So we now
David,
see that.
Sorry,
yes.
We are at about 50 minutes now. So
yes, I'm going to just finish this discussion, and then we will continue with the example at the beginning of the next half. So we've got about another 5 minutes, I think. So we have 2 constraints, one where these these ratios are kind of constrained by root c by the integration, but they're not going to be vastly smaller. On the other hand, the other constraint that we need to require says that the wave packet size times this this inner product has to be much smaller than the scale root c. So that's going to tell us that the when we've chosen a peaking wave function, and we're going to get out the feature that as we need, we have the wave packet size being much smaller than the scattering length. So we need to choose more generally a wave function that has this kind of peaking structure. And of course, we're also taking the limit that c is much less than 1, and we combine these two, we get precisely the set of inequalities that match our physical intuitions from earlier. So let's take I guess about a 6-minute break now. And,
can I ask a question?
Yes.
At this point, so from this computation, you are getting that the wave packet length have to be much smaller than the scattering length, which is impact parameter. But suppose we are considering a scattering process where, like say, head-on kind of collision, but classical scattering process. So can we apply this procedure there, because there the impact parameter will be same as the size of the wave packet?
So that kind of a result is really outside the domain of this approximation. And the point is that imagine if you actually have some finite bodies, 2 neutron stars, you shoot them at each other. If you have a head-on collision, then all of a sudden you actually care about the internal structure. You can't treat them as point particles. And if, on the other hand, they're black holes, well, you're going to get into the strong field regime. Right. So it's a very interesting thing to consider, but it's outside of the domain of the calculation that we're focusing on today.